Hi everyone. So I'm Holly Preece and I'm going to talk to you today about hot subdwarf B stars. So I'm a fourth year PhD student and I'm working at the Cambridge Institute of Astronomy, which is right behind us, and also collaboratively with Armagh Observatory, which is in Northern Ireland. So I work with Professor Chris Tout, who kindly has come along and is right there, and also with Professor Simon Jeffrey, who's in Ireland. So kind of general outline of my talk. First going to give a sort of bit of an overview of stellar evolution. Then I'm going to talk a little bit about hot subdwarf or SDB stars. Then I'm going to talk about tidal interactions. That will just be a sort of general summary. Then I will talk about synchronization timescales for hot subdwarf binaries. And then I will give a conclusion at the end. So first of all, stellar evolution. What even is a star? So the kind of most basic definition of a star is that it's an object that radiates energy from an internal source and it's bound by its own gravity. So this means it's not a planet or a comet. So comets are like bound by their own gravity, but they don't have this internal energy source. And also because stars have this internal energy source, which is nuclear fusion, they evolve in time. So they're born, they die, and they do lots of things in between. So here's a kind of graphic of stellar evolution. So stars start off their life as these molecular gas clouds of gases, which then collapse and condense and form these protostars. Then the stars continue to condense until they have a high enough temperature and density in the core, and they ignite their hydrogen. And they start fusing their hydrogen into helium. So they're sort of like the main thing that tells you what a star is going to do in its life is the initial mass that it starts off with. So stars below 8 solar masses, so it's like 8 times the mass of the sun, are considered low mass stars, and stars above that are high mass stars. So then kind of low mass and high mass stars do quite different things in their life, and they also die in very different ways. So so you can see that. So I'm going to be talking about low mass stars today, so I'm just going to talk about the low mass formation channel. So stars start off with their hydrogen burning core. Eventually they will reach a stage where they've fused all of their hydrogen into helium from the core, and they will move up to become red giants. So they'll kind of turn up towards the red giant branch. And on the red giant, whilst they're doing this, you have the inner regions are collapsing because this big nuclear energy source that you have in the core has stopped. And the outer regions will expand as well. So these cool and expand, which is why red giants are called that. So they get redder as they cool down, and they're also giant. So then kind of towards the end of their lives, they'll generally become a sort of planetary nebula, and then they'll cool down to become a white dwarf. If they're in binaries, these white dwarfs, if they have enough mass, they might explode in a type 1a supernova. So I think 1a supernova was the first one that was like properly observed. So supernova 1987 1a was a really, really exciting supernova. Also happened on my birthday. I wasn't born then, but still. So this is what we call the HR diagram, or the Hertzsprung-Russell diagram. And this is a really typical diagram that you see of observed properties of the stars. So you have surface temperature along the x-axis. Kind of confusingly, you have the low temperature here and the high temperature here. Surface temperature, yeah. And then you have the luminosity along the y-axis. So here you have the hot, dim stars. Here you have the cool, bright stars. So this kind of diagonal that you see across is what you call the main sequence. So this is when the stars are hydrogen burning. And the low mass stars will be here, and the high mass stars will be up here. And then here's the giant branch. So once the stars have finished their evolution or their main sequence phase, they'll move up towards the giant branch. And then the low mass stars will move along the horizontal branch and down the white dwarf cooling track. So SDB stars, or hot subdwarf stars, sit on the extreme horizontal branch, which is right here. So this actually tells you pretty much why they get their name. So they're B classification, which means they have really high surface temperatures. So they have this is like 30,000 Kelvin. And they're subluminous, which means they sit below the main sequence. So a main sequence star with the same color will be much more luminous. So you can see that there's a little gap between this regular horizontal branch and the SDBs, and that's because SDBs are products of binary evolution. So binary evolution, what if there are two stars? One of the most important things that happens is you get mass transfer in between the stars. So this can happen in a few ways. Essentially, it can be stable or unstable. So if it's stable, then your mass, so stars have what you call a Roche lobe, which tells you essentially the distance to which matter is still going to be gravitationally bound. If you have a binary, then they might be close enough that your Roche lobe between the two, especially on the red giant branch when the star is expanding, the outer regions of the star will not be gravitationally bound by the star that they were on, and it'll switch over to the other star, essentially. Your Roche lobe phase can also be unstable. So then your state mass transfer is unstable. And the last thing that I'll talk about is common envelope phase. So this is when you have binaries that are really, really close. And when your star expands on the red giant branch, the outer regions engulf the companion star, and your companion star spends a while going round the inside of the star. And then this matter is all going to be ejected at the end. And you end up with a really, really tight binary. So generally between 0.05 and 10 days in the case of hot subdwarfs. So now my SDB overview. This is the structure of an SDB. So these are stars which have a helium core. And their helium core is about 0.1 solar masses. And this is fusing carbon into oxygen. And it's a convective region. Around the outside, they have an inert helium mantle, which is generally about 0.35 solar masses. And this, as a radius, the entire helium region generally goes up to a bit less than 0.1 solar radii. Then around the outside, you have your low mass but radially extended hydrogen envelope. So even though your hydrogen envelope only has mass of about 0.02 solar masses, it can generally take up more than half of the radius of the star. So general summary of the properties. They have masses peaked at 0.47 solar masses. The radii will be between 0.1 and 0.2 solar radii, and this depends on what happens with your convective, with your common envelope ejection. Just tells you how much of your envelope is left. They have surface temperatures between 20,000 and 40,000 Kelvin, so that's like way hot. They have helium burning cores, which are convective. Low mass radially extended envelopes. They have evolutionary lifetimes of about 100 million years. And they're in binaries. And their companions will either be low mass main sequence stars, generally with masses of about 0.1 solar masses, or white dwarfs. So here I've plotted the orbital period of the binaries and against the companion mass. So there's kind of three distinct populations that you see, or three distinct populations really. So one population has orbital periods of about 0.1 solar days, and they have main sequence companions, which are about 0.1 solar masses. The next population has orbital periods of about 0.3 solar days, 0.3 days, and their companion masses are about 0.4 solar masses. So these ones here. And these are low mass white dwarfs. And the third population have high mass white dwarfs, so kind of between 0.5 and 0.9 solar masses, maybe. And they can be in orbital periods as short as 0.05 days, or 79 minutes. So one system that I am going to talk about quite a bit now is going to be CD-30 11223. So that has a hot subdwarf with a white dwarf companion, which is 0.7 solar masses, and has an orbital period of 79 minutes. So I'm going to talk about tidal interactions. So people will mostly have heard of tides because we have them here on Earth because of the moon. So what essentially happens when you have a companion close to the star is your star gets tidally distorted. So this is a plot with the tidal distortion of a star, an SDB star actually. So the white region is just like your undistorted radius. The blue region is where the radius is compressed, and the red region is where the star is radially extended. So the way that tides work, essentially, or this distortion works, is that when you have your companion, you then have a difference in the gravitational field on the side closest to the companion and furthest away from the companion. And it's this gradient in the potential that makes tides. And this is why we experience tides from the moon and not from the sun, even though the sun is a lot more massive than the moon. So the next thing we'll talk about a bit is tidal dissipation and how that works. So if you start off with a single star, it's just going to be round, no companion. Once you bring a companion close to it, then you get your star being tidally distorted. And if you have no dissipation mechanism, as the stars go around each other, then your bulge is just going to always be continually facing the companion, and it'll kind of instantaneously reshape. And if you do have some sort of dissipation mechanism, then your tidal bulge will either lag away from or lead this companion, and that introduces a torque across the star, which will spin it up or spin it down. So generally, tides will work to bring your system into an equilibrium configuration, and that will be a tidally locked system. So the definition of a tidally locked system is that the stars are rotating synchronously with the orbit. So one spin revolution is the same as one orbital revolution. So the objects take the same amount of time to go around each other, and you just have one part which is always facing each other. So the moon is tidally synchronized with the Earth, but the Earth is not tidally synchronized with the moon, which is why we have the dark side of the moon. So you can only ever see one side of the moon from Earth. Next, the orbit of the binary is circularized, so generally orbits are elliptical. And the third thing is that your spin and your orbital axes will be aligned, so it's all happening in the same plane. So your stars will be rotating about an axis, and they'll be orbiting each other, and your spin and orbit axis are aligned. So your dissipation mechanisms. First is convective dissipation. So this in convective regions, your tides are very efficient. So you have a bulk movement of material moving around the stars. And this makes quite straightforwardly, makes your tidal bulge lag against your rest of the field. The next, you have coupling to the gravitational field. So you get this this happens more in radiative regions, where you have your companion going around the star, and this kind of then gives you a periodically changing gravitational field. So this can be a dissipation mechanism. And you also have, should be Eichmann pumping. You have Eichmann pumping, which is another mechanism. So why is this interesting? In the case of hot subdwarfs, observationally, I said that these stars have low mass main sequence or white dwarf companions, which means that you can generally only see one of the stars if you look at the binary. So orbital periods in general are really easy to measure, like relative to astronomy stuff, and particularly much more easy to measure than your spin periods of the star. So if your star is if you can say that the system is tidally synchronized, then you know your orbital period, and then you also know your spin period, and then you can pretty much solve all of the rest of the stuff for the binary. So that's really nice and great. Also, from a theoretical point of view, these are quite extreme stars, so this makes them quite a good test bed for the synchronization theories. Particularly, synchronization in stars with radiative envelopes has always been a bit difficult. And also, these stars are post-common envelope systems, so post-common envelope is also not particularly well understood phase. And yeah, they're in really close binaries, and also they're compact sources, so these are like the low-mass analogues of neutron stars and black holes. So people have sort of looked at this before, and they looked at the main radiative mechanisms. So you have your Eichmann pumping here, and so this is your orbital period along the x-axis. This is your synchronization time divided by your extreme horizontal branch time. And so this black line tells you if the stars will be synchronized within the extreme horizontal branch time or in the SDB lifetime. So with the Eichmann pumping, they predicted all of the stars would be synchronized. This is just straightforwardly not observed, so that's not what's going on. And then they also, with the coupling to the gravitational field, then they predict that stars with orbital periods of less than 1.2 days would be tidally synchronized. And this is also not really observed. So that kind of works, and you can solve the orbits with this assumption, but the companion masses were really, really massive, like huge, so much bigger than anything that's been observed. So the way that you calculate all this synchronization stuff is quite complicated. So you have this relatively complicated equation with lots of terms, so you need to know quite a lot of things about the system. The main thing that's important is your viscous time, which tells you how your tides relate to the viscous regions. And these are strongly dependent on the separation divided by your radius of your dissipative region. That's to the 6th power. So to find the properties, one of the things that you need to do is solve the second order differential equation. And you need to do that for a detailed stellar model. And the synchronization timescale for the radiative dissipation is pretty similar. So you still have this really strong dependence on your ratio of your regular separation to your dissipation region. And this is also proportional to this E2 parameter. So E2 is really difficult to calculate. You need to solve 2 differential equations for that. So people have generally parameterized it by just saying that your E2 is your radius of your convective region divided by your total radius of the star to the 8th power. So this doesn't work really at all well. So here I've got my radius of my convective region divided by my radius of the SDB. I have a grid of models. I've got I don't know, about 500 models maybe here. And then I have my log to base 10 of the E2 along the x-axis. So this line is if I calculate the E2 by solving the differential equations, and this one is if I calculate it just with the parameterization. And what you find is essentially 4 orders of magnitude difference. So the E2 is 4 orders of magnitude smaller if you calculate it properly. So the way that this then applies to the tides, if I apply this to the CD minus 30 11223 system, which is the one in a really tight orbit with a really big companion. So here I've got my convective radius ratio on the x-axis, and then here I've got my synchronization time on the y-axis, and this dotted line is the extreme horizontal branch lifetime. So if you don't do your detailed calculation of E2, then all of the models sit really well below this horizontal branch lifetime. And if you do the detailed calculation, then they all sit far above the synchronization timescale. So even the most extreme system is still not tidally synchronized by this mechanism. It's also kind of important to notice that even though the radius of the convective region changes a lot, the synchronization timescale only changes by about an order of magnitude. So if I then include convective dissipation for all of the models sits along this diagonal line down here. So you can see that most of the models are synchronized, essentially, apart from the ones with the really big envelopes. So these ones where you have a small RC over R have big envelopes, and these ones have small envelopes, more or less. So then I kind of took one of the models down here, and I applied it to the whole set of hot subdwarfs to try and predict which of the stars you can say are synchronized and which ones aren't synchronized. And essentially only these 3 with the high mass white dwarf companions fell inside the contour. And all of the rest of them sit outside of the contour, so these are not synchronized. So it turns out it's actually a little bit more complicated than that. So because these are in really, really tight orbits, then the companion is moving around the star more quickly than the convective region is moving. And this means that your tides are dissipated a lot less efficiently, to the point where actually even these are quite likely not synchronized, and if they are, then it'll only happen right towards the end of the star's lifetime. So really just broadly, synchronization is not a good assumption to make. So one thing I spent quite a bit of time looking at was what you can do to the models to make them synchronized. So along here I again have my radius of my convective region. So our idea was that if you just increase the radius of the convective region, then you have a bigger dissipative region. The tides will be dissipated more. And and that'll be great. So even that didn't actually work particularly well. So even if you make the entire helium region convective, then the stars are generally not synchronized. And essentially, the thing that it comes down to really is the way that you treat the viscosity within the star. So along here, this dashed line is the critical viscous time for all of the different radii of the star. And then these points, different models and different convective treatments of the star. So essentially, what you need to happen for synchronization is for the convective material to be moving fast enough that the convective region is moving faster than your tide. And then you will probably get synchronization, especially if you then have an enhanced core size. But whether or how valid that is sort of uncertain. There's some hydrodynamic simulations which suggest that the convective material is moving much faster, but that's not super conclusive still. So my general conclusion, are stars tidally synchronized? No. Actually, if we totally change the way we treat convection and only look at the closest systems with the highest mass companions and only look at the most efficient models, then possibly maybe they can just about be synchronized. So basically no. So thanks for coming to my talk, everyone.